Hello everyone, a very good afternoon to all of you. I am Priyanshi, welcoming you all on behalf of Wind Insider and First View Group to our webinar on Wind Turbine Tech, highly efficient, reliable turbine design and engineering services. Thank you all the attendees for joining us today. I hope all the attendees had a great time in networking with your peers in our exhibition tables. Let me quickly take you to an overview of today's event. This webinar will provide an overview of how modern wind turbines and increasingly cost efficient and more reliable. This event will take you through the development of longer, lighter rotor blades, taller towers, more reliable drivetrains, and performance optimizing control systems. Now, I take the pleasure to thank our sponsor, Platinum Partner Hexagon, for extending their immense support to organize this event. I request my team to play the sponsor video of our Platinum Partner Hexagon.
Manufacturers today are looking for smarter ways to improve quality and productivity. Hexagon is a global leader in digital solutions that create autonomous connected ecosystems where data is connected seamlessly, converging the physical and digital worlds and building intelligence into all processes. Exalt, Hexagon's framework for using IoT data to accelerate digital transformation, provides a base of technologies like cloud computing and artificial intelligence, which enable our smart manufacturing solutions. Hexagon's Manufacturing Intelligence division is digitally transforming manufacturing by converging design and engineering, production and metrology solutions to make our customers' factories smarter. Our design and engineering solutions use computer-aided engineering techniques to simulate reality, so quality is embedded into product design and manufacturability is guaranteed. Our production solutions include CNC simulation and computer-aided manufacturing software that ensure design intent is maintained through the production process, improving productivity and delivering high-quality components. Our metrology sensors capture real-world data for positioning and inspection, while metrology software provides actionable information through advanced analytics and intuitive reporting. Hexagon's expertise in sensor technologies, software and data orchestration enables autonomous connected ecosystems for suppliers and customers, improving quality and productivity by making your factory smarter.
Thank you so much, team, for playing the sponsor videos. So now we are having a sponsor presentation by Mr. Naveen Chakradhar, who is the Senior Manager, Technical and Business Development from Hexagon Manufacturing Intelligence. So I request you, sir, to please share your screen and start with your presentation.
Priyanshi, can you confirm if my screen is
Sir, we cannot hear you properly. Can you
is
turn
it
off
good
your
for you?
camera once your network is fluctuating?
Hello.
Yes, sir. Yes, sir. Can you start with your presentation? Naveen, sir, can you hear us? So, Naveen, sir, is facing some technical issue. Never mind, we can have his presentation after he comes back online. And so, with this, we will move ahead with our much awaited panel discussion, which is on wind turbine tech, highly efficient, reliable turbine design, and engineering services. And to discuss this, we have in the panel with us Mr. YVR Vijay, who is the ex COO of Suzlon and also the moderator for today, Mr. Amol Korde, who is the head software and consultancy from Hexagon, Mr. Gopan PR, who is the country head products and solutions of Envision Energy, Mr. Satish Subbarao, who is the head engineering from Aprava Energies, Mr. Manjeet Bhagria, who is the head of operations and maintenance from Inox Wind, and Mr. Rajiv BC, who is the senior manager of LM Wind Power. Now I welcome all the panelists on the screen and requesting Vijay sir to lead the discussion.
Yeah, good afternoon, everybody. So, special good afternoon to this distinguished panel that we have here. And today we'll be talking on various issues relating to design, development, and operations of the wind turbines, the latest trends in this. And as you can see, the last 1 month has shown how much the world is still dependent on oil and gas. The world is practically being held to a blackmail by big powers, politics, etc., going on, and every country's development and life gets affected due to this. It makes it all the more important that we get into a clean energy concept, we get into renewable energy where each country is totally self sufficient on its energy resources in the form of renewable energy. And wind energy plays a very significant part of this whole clean energy. In fact, wind energy, as you know, in India is almost now at 50-50, with solar growing very fast. Solar is practically growing at doubling every 2 years, and wind is increasing at around 10% a year. But we need to speed up that and get into the latest technologies on wind. So, today in our panel discussion, we'll be discussing these major advances which are going on and focusing it on India. So, we would be discussing what are the bigger blades in the market. What are the bigger blades in demand now? As you know, the sub 60-meter blades are out. It's all 60-meter plus 60, 70, 80-meter blades which are coming into India. And in Europe, you're already seeing the 100-meter plus blades. You're seeing taller towers. The 120 meters is the base height of most of the towers today which are in the market. You're seeing turbines which have much more efficiency and annualized estimated energy production. You're seeing PLFs of over 40%. Nobody talks of turbines with plant load factor less than 40%. You're seeing various trends on on-site assembly, on on-site construction of these wind turbines. A major project coming up is with the wind turbine repowering. The older sites, which are the best windy sites, can now be, people are looking at how to increase the energy production from here by putting bigger, better turbines in these places. We are looking at turbine performance optimization using various softwares and control systems, data analytics, etc. There are advanced logistic systems in place to enable quicker construction of wind farms. We have a lot of studies going on load management and using load management to design better turbines. So we low wind specific turbines, typhoon specific, high typhoon area specific turbines, turbines for near offshore, turbines for far offshore, and we're also looking at modularization of turbines. So there's a huge range of advances which are going on, and today's panel will address some, if not many, of these issues with the help of the depth of the knowledge that they have. So I think, could we have Naveen? Are you ready with your presentation, or should we start the
Yeah,
panel?
yeah, I'm back. Excuses for the network issue. Yeah,
Yeah. So should we see Naveen's presentation and then get on to the panel discussion?
Yes, sure, that would be great.
Yeah.
yeah. So, can you confirm me, sir, like if you're able to see the screen?
Yes, we can see the screen.
Okay. So, good afternoon, all. Thank you for setting the stage for me, sir. So, good afternoon, all. Welcome to Wind Turbine Tech. I'm Naveen, Senior Manager at Hexagon Manufacturing Intelligence, and I'm responsible for renewable energy business. So, sustainable future is what brings us all here, as Mr. Vijay was saying. And as wind turbine plays a key role in harnessing energy from wind, its reliability is becoming very important. So, wind turbine design is evolving rapidly with increased tower heights and rotor diameters and increase in size also. And increase in size also means increase in
I think your connectivity is weak, Naveen. You're again off.
Vijay sir, you can continue with the panel discussion, and after the panel discussion, we can have Naveen sir's presentation.
Okay. Okay, fine. So we will get into the panel
Since his
discussion.
network is fluctuating.
Yeah. So my first initial questions to the panel is, let us look at the start point as to how do you convert your, as to how do we, these wind loads that are there, how do you model this and design, put it into the design so that you come up with the wind turbine design from wind loads? Amol or Naveen, can you
Yeah,
tackle this? Yeah.
yeah. So see, basically what happens, any design starts with the working loading conditions. If we do not know the loads, we can't design reliably. And the assumptions about the loading is the biggest culprit in the wrong designs. So keeping that in mind, there are various concepts came up for the wind turbine design. Although this technique is been widely used in automotive as well as in aerospace and uh, elsewhere. So the best way is to actually measure the load and apply it. But usually what happens when the things are in dynamic condition, such as automotive or wind turbine, the load is not constant. The torque is varying across the wind conditions, and then there are different wind conditions as well prevailing across the globe. Even if we consider India alone, the different wind conditions poses different torques, different RPMs, and the different durations of time. Now, if I give you the situation before I explain that how to actually capture the right wind loads, the situation is if you try to measure the torque, power, and RPM for that matter for any rotating component, you will end up having billions of data points. For example, your turbine may rotate at maybe uh, 3000 Newton meter torque for 10 RPM for 1 minute. Similarly, there may be x Newton meters of torque, y amount of duration, and z amount of RPM. So these billion data points actually has to be converted into a handful of load cases. So what is the best technique available today? Is people still go? That is surprising thing that people still go with certain binning methods or certain assumptions based on the statistical data. Now, what is the very innovative and reliable and very scientific method which has been developed at Hexagon Manufacturing Intelligence is that you collect the wind load data. Nowadays, there is a wonderful technique available that you can actually model the wind turbine with simulation methods, which we all know. You can simulate the various wind conditions on the software programs, and then with these wind conditions, you can actually capture the different loading conditions by means of simulation itself. Now, if I go alone with the test data itself, for example, if I put some instruments on the wind turbine, uh, maybe a 1 megawatt wind turbine or 1.5 megawatts of wind turbine in certain areas of India, and then capture the wind loading conditions, then I would have billion data point data sets in various wind conditions. Now, what I do is I have a simulation model of a wind turbine where I have modeled everything gears, bearings, and shafts, and all that kinematic which is in working condition, and it will actually simulate the real time data. Now, that model will apply these billion data points under the direct fatigue simulation, then we'll calculate the damage and life for the bearings and gears. On one side, we'll keep the damage and life of a billion data points, and on one side, we'll apply the some using some smart algorithms will find out the right load cases on the wind turbine, will calculate the damage and life of the simulated load conditions. Now, post that, we'll compare the damage of billion data points and damage of simulated load cases. If these two matches together, then one can confirmly claim that whatever the duty cycle I have simulated actually represents the billion data point. So this is in a nutshell. This is the technique, and this is widely been used in aerospace and in automotive since last you can say 8 to 10 years, and in wind turbine also we have proved it. The I must tell you what are the challenges in this technique, because people still believe that simple binning method that if I segment the torque bins, say maybe from 100 to 200 Newton meter, 200 to 300 Newton meter, and so on, up to the maximum rated torque condition of a wind turbine, and then take the mean torque of each bin, and then just add up the duration. So that has its own limitation, because here we are not considering all the comprehensive effect of the entire system which is in place. Now, what does it really mean by comprehensive system loading conditions? In a simple way, it is basically the wind turbine gearbox and the generator or the entire system is actually a flexible body which undergoes lot of deflection and stresses, which ultimately puts the different loading conditions on the gears and bearing. Ultimately, the bearing and gears are bound to have certain amount of misalignments in real life loading conditions. So considering all real life behavior or the physics of the gears and bearing, and then account for the damages and the lives, and then claiming the billion data points is equivalent to the handful of load conditions. For the people who are watching these program, those who are into design, they would clearly know that when they actually want to simulate the wind turbine loading conditions, they would simply come up the wind gust loads or wind loads in terms of Newton meter, in terms of RPM and the duration. And then they put set of load conditions. So that there may have 25 load conditions or 100 load conditions. But what is the guarantee that these set of load conditions would actually represent the billion data points? So in a way, there is a technique and we call it as a duty cycle condensation. So condensation literally means how we condense the vapor in a small droplets. We are condensing billions of load cases into small handful of load cases. So duty cycle condensation is a term which is now available for wind turbine designers, by which you can accurately predict, apply those load conditions to the wind turbine, and then design the wind turbine, and thus you can improve the reliability of wind turbines. So basically, this is in a nutshell. This is the technology available.
Thank you. That was really enlightening. So, before we come into the wind loads as such, the most important factor would be the assessment of the wind resource as an assessment. A wind resource assessment is a very key factor before we decide where to put up these turbines, understand what are the wind loads which come up in these areas. So we have with us an expert who's been for a huge time in product development in the wind industry, Mr. Gopan PR. So if you could bring out to us, Gopan, on the importance of wind resource assessment, especially with respect to wind resource assessment with respect to India, how much efficiency we can expect, and what sort of outputs can we expect from wind turbines in India? Yeah.
Okay, thank you, Vijay. It was really a good question because there we start on the wind assessment because this is an important topic. Whenever we want to set up a wind farm, we need to do the wind assessment as well as we need to check the suitability of the turbine which has to go into that wind farm. So this is the major two things which we need to focus on. So coming to the wind assessment, as you also were mentioning that there are a lot of advanced tools available for the wind assessment. So it is a time now where we can assess the annual energy production in a more reliable way. And we have very advanced reliable tools. Some of the tools like CFD based tools, which has more accuracy, means when I say more accuracy, it will predict to a closer level to the actual the generation can happen. So that type of advanced reliable tools are available in the market. And then definitely a proper micro sighting really helps because as you know that the wind terrain varies. Some terrain may be a flat terrain, some may be something like a semi-complex or a complex terrain. So microsighting is very important. We need to put the turbine at a right location so that whatever the wake related impacts are coming on the turbine, that is to some extent it can be reduced. The wake losses can be reduced. So that way, if you can reduce the wake loss during the planning stage, during the micro sighting stage of the wind farm itself. So that really helps in two aspects. One is that definitely the AEP, the estimation is better, and then for the operational life of the turbine, you will have lesser wake. So the AEP generation is better. Apart from that, the loads which is coming because of the wake, that is also reduced. So that will really help to operate the machine for a longer period, especially the operational life of 25 years. And we will see that issues related to the component replacement, all replacement may also get reduced because the loads are relatively lower. So this is what generally it happens. And these turbines has to operate for 25 years and we need to see that this is the energy assessment, what is the IRR or business sense to put this turbine or develop a wind farm. So energy estimate if you do basis that, because this is also a key element to understand what is the cost of energy, because we need to really know upfront what will be the cost of energy, and basis that the real business call can be taken. So this all helps. Apart from that, when we talk about the suitability of the turbine for particular wind condition that need to be assessed, then we can evaluate which turbine is more suitable for specific wind conditions. Basis that, we can also come out with a site-specific power curve so that we can have a better yield from the turbine. Apart from that, we can also evaluate what could be the site-specific tower. So the tower height should be like 120 meter or 130 or 140, depending on the wind conditions. Mainly, if the shear is more, it really helps, and then basically that helps us to see that how much hub height we should keep. Otherwise, we go with a higher height, and then if the shears are low, then the advantages are missing there. So generally, we see that with every 10-meter increase in the hub height, we get 3 to 4%. As a thumb rule, we say that 3 to 4% increase in AP. But then it depends upon the wind condition and the shear and the turbulence. So understanding the wind is important, and then putting a turbine at a right location is important. Selecting the turbine is an important. So these are the basic three things which has to be taken care. And to have a reduced cost of energy, definitely we need to have the proper optimized hub height. So that really helps. So these are the major things which really helps for the assessment of the wind as well as the turbine suitability study.
Wow, thank you. Thanks. So, as we are seeing now, the trend in when I really started, I entered into the wind industry. Those days, the type of turbines had blade lengths of around between 25 to maximum 40-meter blade length. That's about 10 years back. But today, we are seeing that those are all history. The minimum blade lengths today, which are being introduced in India, are above 60 meters. There are very few turbines which have a rotor dia of less than 120 meters in India. We are seeing introduction of the 140 plus rotor dia blades. We are seeing even 155 rotor dia blades. Some companies are wanting to. So there must be a lot of change in blade design and manufacturing technology. So we have with us Rajiv from LM Wind. Well, Rajiv, I would like to ask you what are the latest advanced blade design and manufacturing technologies? Because that is the first place where the loads are starting to be felt on a turbine, with large blades in we are talking of 60, 70, 80-meter blade lengths in India. So what are the advanced blade design and manufacturing technologies which are coming
Yeah,
up? And what would be these blade lengths? What sort of are in demand in India? And what sort of pressure are they? How do they affect the structures?
definitely. I think it's a very good question and a
Sorry to
very
interrupt. Extremely
sorry.
sorry to interrupt.
Yeah,
Vijay sir, after we have Rajiv sir's insights and his point of view, we can also have Naveen sir's presentation since his network is stable now.
right.
So first you can have a discussion with Rajiv sir. Please take it ahead.
Yeah,
Yeah, thanks, Priyanshi. So I see this, Vijay, as a very heavily loaded question. So I would like to kind of break it down into small chunks and try to answer them as much
yes,
as possible. As Gopan and Amol mentioned, from the upstream side, once the loads and wind assessments are formed up, it gets transformed into wind loads for us, the operational loads, or it could be the design extreme loads. And then the customer reaches out to us in terms of what kind of lengths they are looking, what's the hub height, as Gopan mentioned. And then through our iterative conceptual design process, we kind of form up a kind of a architecture which is typically a standard one for our customers. And off late, compared to over the last 5 years, there has been drastic changes which are coming up from the customers in terms of two parameters. Basically, these two are how to maximize the AP and how to minimize the landed cost for the turbine. And blade becomes a very critical component component which goes into the cost model in terms of a LCOE. So technologies need to improvise, technologies need to change every day, and it is a very rapidly changing environment for us. From the blade design side, advanced in terms of the design methodology and the design blade designs for certification and going beyond certification, trying to understand the thresholds. These are some things which are putting us new challenges in terms of blade design advances. What is happening in the latest recent times? The blade lengths are becoming larger. The demand for low weight and kind of a competitive cost puts us into a situation where we need to test the materials which go into the blade at a very coupon level or a substructure level, and demonstrate the reliability of those materials which get into these advanced blades. So the test campaign has become much more robust. Test campaign is now getting into more artificial intelligence based or simulation based kind of approach that helps us to accelerate the test campaign, test programs. And that once the materials and the design allowables are available for us, we are now using a lot of automation into our design process, blade design process. A lot of digital methods are being applied, and also we are moving further in terms of how the aerodynamic design expertise which we have accumulated over the last 30 to 40 years, it has been transforming, and major transformations are happening in terms of the way we simulate the blade geometry, the blade properties. It is getting really into kind of a best in class of late, and it also puts us into kind of using more aggressive targets for ourselves in terms of it could be mass, it could be frequencies, and we try different variations, different architecture, which is all possible because of the way we have automated our process in the current design process. Moving to the right side, on the manufacturing side, on the advancement, we are learning a lot of new things in the last 3 to 5 years, especially in terms of how to handle carbon, how to get modular in terms of our tooling. That's very critical for us because the kind of cycle times which are being demanded by customers for commissioning the projects are really aggressive these days, and it puts a lot of pressure onto our manufacturing processes, which needs to get a lot of automation. As we all know, blade manufacturing process has been historically and traditionally very manual process. It depends a lot on workmanship of the operators or the technicians. We are moving into a direction of a lot of data gathering, data crunching, and trying to use the data and build more artificial intelligence into our manufacturing process. That's the way in which our manufacturing direction, manufacturing advances are leading towards. It all typically boils down to how we manage the cycle time, how we ensure that the quality of the blades are not kind of impacted while the delivery schedules and pressures are being felt. So a lot of modularization is helping us, and that's one thing which I would like to call out. So that's how these two areas of design and manufacturing advancements are helping us to keep up to the expectation. Otherwise we will not be able to kind of build blades which are really reliable, which are really in terms of best in class in terms of quality, and also they perform to the expectations of our customers in terms of AEP, which I mentioned at the beginning of my response to this question, Vijay. So that's how I would like to kind of summarize the advances in blade design and manufacturing.
Thank you. So, Naveen, can we now get on to
Yes.
the presentation?
Yes.
Thanks, Rajiv. That was very good.
Can you confirm me, sir? I'm audible?
Yes.
Yes. Thank you all. Excuses as I don't know how much of my slide you could hear earlier. I had some network issue, and I would like to continue with from where Mr. Amol, Mr. Gopan, and Rajiv had talked about on few points. So while I start again here. So, good morning. Myself, I'm Naveen from Hexagon Manufacturing Intelligence. Uh, as we all here are there for sustainable future, I want to mention that wind turbine plays a key role in harnessing energy from wind, and so its reliability is becoming very important. So wind turbine design is evolving rapidly with increased tower heights, rotor diameter, increase in size, also increases the loads on the turbine components. So Mr. Rajiv also mentioned about this, and especially the rotors and drivetrain components are becoming very susceptible to failures. So the increased load has led to use of new rotor materials and innovative rotor designs and manufacturing technologies. So let's, in my coming few slides, we'll be covering these points, which already you would have heard from Mr. Rajiv and Mr. Gopan, who mentioned in the few earlier minutes. So I know wind energy is been known to everyone, but most of you would not know who Hexagon is and what we are. So I just want to touch upon this with this slide. Our legacy has always been linked to data. We emerged as a leader in sensor solutions that enable the digital capture and that enable the digital capturing of the environment and positioning of the physical world. We later added software solutions to not only unlock the value of sensor data, but also to offer ability to design and simulate and provide location intelligence of real world scenarios. And today we are combining these things like machine learning and artificial intelligence with sensors and software leadership to create powerful autonomous solutions. So I take huge pride in ourselves that we are moving towards bridging the gap between the digital and the physical real world. So by from concept design to the real world products side. So we all know this that there is a huge demand, and roughly we have to scale up by 10 times to address this by 2050. So we need to get better products out faster, and there are many unknowns. Therefore, model-based development techniques are very essential. We heard from Mr. Rajiv that they are looking at. They have been doing a lot of earlier from manual to they have moved to automation, working on the material to reduce the weight. So we will see the same points coming up in my slide over a few minutes. So while the demand is there, to address the demand, we see that the turbines are becoming very big, as I mentioned. In the earlier days, we had seen that the rotor was 30-meter and roughly it was providing 300 kilowatt power. But now it's the size of the rotor has gone up to 200 meters, and where we are seeing is 12 to 20 megawatt uh, uh, supply. And in this, we have seen that onshore wind turbines create other different challenges. So we have to move towards offshore. And again, offshore has its own issues, like you cannot put them on the seashore. There's a lot of issue in transferring and assembling them. So it brings a lot of technical challenges and manufacturing challenges. So we will see this, how to address this. So when we look at with the increase in size and uh, blade size are becoming bigger. Hello.
Yeah, we can hear you.
So there are a lot of mechanical failures happening. It could be the blade is hitting because of its size growth. It's getting flexible. It's too huge, heavy. So it comes in contact with the tower and hits. So then there could be a bird strike, or it could be thermal issues. The gearbox is failing. There could be a fatigue issue over the years, or there could be lightning strike and acoustics. So these are different kinds of challenges and issues we are seeing over the years. And how do we address this? Obviously, there are technical challenges and commercial challenges. When you say technical, it's more on the durability, efficiency, and acoustic, more on the dynamics and acoustic side. And commercial challenges are like you need to the cost of energy production. We need to address maintenance, reliability, and reduce time to market to come up with new designs as early as possible. So, when we look back and the lessons what we have learned, we have seen that after we have manufacture products, we tend to understand that there's a lot of rework and we have to improve the designs. So that's where we again go back to the initial stage. So what we are trying to do is, instead of reworking, what we are trying to tell you is why don't you bring the design in the upfront and try to do a pre-work then instead of rework. So with this slide, this is a comprehensive technology map that shows how hexagon technology can be applied to improve different aspects of the wind turbine design, manufacturing, and inspection. As you notice, we have unique position working both in virtual side, that is all through simulations, and the real side, that is where we are helping as whatever has been designed and manufactured, we are able to also measure the quality that they are being designed properly. So if you look at the blade, we can study anything from what materials to choose for constructing the blades, to blade dynamics, extreme load prediction, blade fatigue, crack propagation, to analyze the blade aeroacoustics, minimizing the wind noise, all the way to the blade inspection before the installation. So let's look into each of these areas going forward. So as you see on the top left corner, I'm just trying to say here that this chart describes the relative capital cost of equipment, and we see that 90% of the equipment value is being shared by blade, tower, and nacelle. Where nacelle, I say, it's also the drivetrain. So 52% constitutes to basically the drivetrain. So, and on the right side of my top slide, here I'm trying to tell you that on when we look at the downtime or the failures is more happening in the gearbox. 78% is in the onshore we are seeing, and 70 close to the same for the offshore as well. So there is a lot of need to address this failures in the gearbox and the bearings, which is the heart of the wind turbine. So where we look at our solutions like Romax has proven experience at the leading edge of drivetrain design. So you, as a designers, like today, engineers can question like, how do I choose the best drivetrain concept? Like they can look at how do you explore any design variants, how do I select and design rotor bearings, then what is the influence of surrounding structure, how do I optimize the stiffness of my housing and minimize gear misalignment. So all these kind of questions can be well answered, and the same goes for the bearing as well. So you don't need to make a prototype, test them, and then realize that there is an issue. So these things can be addressed well before you end up designing your products. So the same, I would like to go into little detail with a closer look of the model-led drivetrain design process. In the early stage, it's necessary to quickly evaluate and compare many designs to explore the design space and select the best concept layout. So if you see here, as we go in the design process, we are able to bring into different complexities like we can it's not only just subsystem level on the drivetrain, we can also introduce the whole wind turbine and the effect of wind turbine or other subsystems effect into the drivetrain, and how that influences in the for the contribution of the loads. And then based on this, it's not only that, even in the design stage we address issues like acoustics, thermal stress, and fatigue at very initial level. And meanwhile, also parallelly, we take inputs from the measurement directly into Romax. So this completely covers a tool, basically a loop, which will help designers to come up with better designs very early in the stage without any reliability issues. So when I come to Blade, I think Mr. Rajiv already mentioned. Let me just again reiterate: as the demand is there for bigger blades now, because it can sweep more power, and then while at the same time, as it is becoming bigger, its weight is also increasing, and then that's leading to come up with new designs from the composite side, and developing stronger and lighter composite materials. So that's where we have solutions which you see we go down to the micro level of the component, where we can help to design continuous fibers, woven fibers, or you name it. We help engineers to simulate complex hybrid material combinations by counting local material performance while performing larger component scale simulations. So even we have seen there are also stress on recyclability of the blades. So that's where material plays a very important. So these things can be well addressed, and I'm sure we know Mr. Rajiv is already using these solutions, and yeah. So And again, coming to acoustics, when we say acoustics, as the size of the blade turbines are becoming bigger, so there are a lot of noise, which we say noises, which is not good to hear. So it could be either due to aerodynamic, that is we call aeroacoustics, or vibro, that is due to the mechanical interactions, which is a source coming from gearbox. So these are causing a lot of noise, and that's making these wind turbines to be placed very far from the villages. So what you see here now is roughly a 230 turbine, which is close to two soccer field put together. And the kind of noise it creates, it's challenging to address this. So what we do is, as you see here, we can virtually bring these uh, uh, concerns into the virtual domain. We can try it out with changing the blade aerodynamic profile, and then see how this contributes to reducing the noise. Or it could be on the panels, like on the nacelle, like you try to put some perforated layers and see that, okay, if you can absorb some sound within the nacelle itself, instead of transferring it to the exterior area. So this kind of, as you see here, the video which is running on the right corner of the bottom screen is where we are trying to simulate through acoustics, in the acoustic domain, how we create some microphones and measure the sound which is getting emitted out. So, and again, as you see here, this is with different material, how it's trying to absorb. That is what is shown in the top screen. So as we move from acoustics, I would like to also mention on the CFD side, here we have picked few topics where we would like to explain how CFD and CA solutions can bring value first to tackle blade designs. That's where Rajiv also mentioned this becomes very critical. The second challenge is about floating wind turbines, and how to take account their complex environment. Last one is about how to design full wind farm. So here, on the floating offshore wind turbine, I would like to mention that we also have some discrete elements to model the mooring lines and then structure, so that then it introduces a better, higher fidelity model, where we introduce the aerodynamic load, wind load, wave loads, and then see the stability of this wind turbine or the output of this in these scenarios. And while also we see that there's huge thermal issues getting seen into the nacelle because of a lot of interaction. So these thermal issues cause a lot of failures. So we have to look at how we can transfer this heat out of the nacelle. So that's again a key important area. So what you see in the bottom right corner is, with our hexagon geospatial products, we can also map the whole terrain. And then we take that whole terrain into the virtual domain. I think Mr. Gopan was saying, how do you assess the wind farm? So this, I think this would rightly address that. So while as a wind turbine alone, we can do a lot of studies, but when we try to put these wind turbines as a farm on different terrain with uneven ground, so you would see that its performance keeps changing. So that's one key area which is very much important. I think he mentioned very well, and I think this actually addresses that concern. So again, with these, I would like to also mention, when you talk about wind turbine placement in the wind farm, one was on the with respect to the different terrain, but here what I'm showing is, when placing multiple wind turbines, it's important to minimize the impact of wind turbine wakes. This is also mentioned by Mr. Gopan in his last statements. Indeed, it represents about 15% of loss of energy produced in the farm. So representing a real 3D CFD wind turbine farm won't be realistic due to the size, due to the model size. And when you look at here, we are having close to some, uh, when there are huge number of wind in the wind farm, it becomes computationally very difficult to compute this. So what we do is, we have we are trying to optimize this based on like we have brought machine learning program into us what we have as ODC. Here we did a simulation of a pair of wind turbines with real 3D shape. We fulfilled the DOE by changing parameters permitting to build a reduced order model. So what you see here is we are creating a reduced order model of the wind farm, and then where CFD simulation was lasting earlier was lasting hours with ODC, our optimization tool, we were able to visualize the impact of the distance between each wind turbine in few seconds. So if you see here, I hope you can see 1 second on the right is the video playing. Yeah, we can see that within few seconds we can try to configure place different wind turbines and see which is the maximum best position for these wind turbines. So, and again, I would like to use this which I video from YouTube. I think Mr. Rajiv can explain more about this. So let me play this while I'm playing. Can you confirm if I'm audible?
You are audible.
Okay. So here we are seeing an actual physical test of the blade, which is being done in LM Wind. So it's a huge blade. It was very nice to see. I put the link to see this with the audio. So what we are seeing is, let me just forward it. They are trying to apply a huge wind gust that is either kind of load coming from the wind forces, or it could be the rotor load, which is again coming roughly. It's roughly around 100 kilometers per hour speed of wind, and roughly I think 280 kilometers of per hour of forces coming from the rotor. So these two are get introduced into this test train, and they're trying to simulate how it performs in this cases of with respect to fatigue. So what I'm trying to mention here is these kind of test is very well required, and we are not trying to eradicate this. But what I'm trying to emphasize is with simulation, what you see in the right side, we are what the engineers can do is, as of today, you can do a lot of what if analysis, and then you can go into the physical domain after you have come up with the best design, because the physical domain doesn't give you more space to work with multiple design iterations, because it's too cost the time and cost of doing a physical test is very much, and you cannot come up with better designs quickly. So with this I just want to go to the next on talking about fatigue. So this is a very important topic for wind turbine engineers. Like what we
Naveen
see here.
sir,
Yeah,
sorry to interrupt you. Can you wrap up the
yeah.
presentation a little?
Sure, sure. Yeah. So here I'm just saying, like wind turbine in its service life of 20 years, it experiences different kind of load. So fatigue plays a very important role, and this can help to quickly understand what is the kind of failures happening on the wind turbine by putting all the historical data what you have, and then look at each the system and subsystem level. And this is a total loop of I'm just trying to touch upon what Hexagon can address with their solutions. And it's not just simulation. We also have solutions where after you design and manufacture, we are helping customers with inspection or during installation of their wind turbines. We can help them. And I would like to just, I have just two or three slides more. I would like to mention that it's not just design or the simulation products we have. We are also into providing engineering services. As you see in the slide, by applying our tools and knowledge and process, we are helping companies to design and certify. Like if you see 38 plus certifications from GLA design assessment are awarded to us. 10 plus patents are approved and pending. 30 plus supplier selections, support for bearings and gearboxes. 32 new designs for gearbox development projects. 8 plus gigawatt of assessment worldwide in analysis service has been done using our solutions. So we have almost helped 10 plus countries in geographic coverage. So with this, I just would like to end my presentation by saying that we cover the whole portfolio from design to manufacture to lifetime of on the physical aspect. So with this, I end my presentation. Thank you. Please feel free to reach out to me later if you have any questions or post the questions. Thank you. I think you can take over for the panel session from now.
Yeah, thank you. Thanks, Naveen. That was
Yeah.
very impressive, the work being done by Hexagon. So my next question is to Satish. He's a veteran of the power industry, the oil and gas industry, renewables, served in a number of top wind industries across. We are seeing now suddenly, we are only talking of 100 to 200 meter long blades, rotor blade lengths. We're talking of towers 100 to 200 meters. What is the limits to this upscaling of wind turbine? And there's a huge logistic challenge which comes up. So are we seeing anything with modular blade developments coming up? And or are we ready now? The world is ready to see some radical design changes which may come about. Yes, Satish, over to you.
Yeah. Thank you, Vijay. So, from an IPP point of view, upscaling is always good news because where you could previously install three turbines, you only have to install one, for example, and that's good news. Capex is less and OPEX is also less. But what happens is this cannot continue forever. So I saw a prediction by TTU. It said that by 2035 we could have reached 276 meter rotor diameter, and apparently we are going to hit the plateau soon. So for an onshore wind farm, even assuming we can manufacture these, design and manufacture these blades, logistics is going to create a huge bottleneck, though you cannot say the same for offshore, where it may still be possible. You don't have to go through narrow lanes to reach your location, so it may still be possible. So upscaling does present a problem unless we can have a jointed blade design, or and if we can have this jointed blade design, then it's possible that we could realize the benefits of upscaling in onshore wind farms. As far as radical designs coming up in this was something we had not expected. So we thought it is only this one-way track, increase rotor size, increase the hub height, and get more megawatts out. But now we are beginning to see some constraints in doing that. As the rotor dia increases, we expect that the tip speeds will get so large that you'll have to reduce the RPM, and then the blade designers are shifting this problem to the drivetrain, because once the RPM reduces, then you have to have more torque, which needs to be handled by the gearboxes. So all this then further increases the weight of the nacelle. So there is some discussion on how to reduce this, and this may probably be even tried initially in the offshore sector. And in this concept, you actually have the rotors on the tip of the blade. So what happens is you have three rotors there, and which since they move at the tip speed of the blade, you can have these smaller rotors. They can be smaller in diameter, and they can have a higher RPM, and all this eventually is expected to reduce the weight by at least 50%. So this sounds radical. Probably people may wonder, how are you going to evacuate the power from these small generators which are mounted far away on the tip of the blades, and or in this case, the blade becomes this large blade is the primary rotor. So from the secondary rotor, how are you going to transfer the energy? And we all know the tip of the blade is also is subject to lightning. So how do you deal with these things? Will it cause the failure of the entire generator itself? And how do you evacuate all that power you know from these individual rotors? So what kind of cabling and all this has to pass through the blades? So these are some questions that will have to be addressed. And the other thing that I wanted to just discuss was and Vijay, you actually mentioned it in your introduction, is the low wind turbine. So at least in the context of India, we clearly have two demarcated seasons, high wind and low wind. And so for good part of the year, so almost for 6 months, we have this low wind scenario. So the turbines that we have currently, they don't do that well in this low wind. And the concept is, which was originally thought of by some designers, was to actually develop these low wind turbines more as a solution for a peak power shaving on the grids, because all turbines start delivering their maximum power at exactly the same wind speed. So that becomes a huge problem for the grid management. And we are already seeing its effect. A lot of us are subject to curtailments. So one solution is, if you have two kinds of turbine in a wind farm, so the ones that we have now, let's say we call them the conventional turbines, which reach rated output at say 10 to 12 meters per second. Then we have another set of turbines, uh, which actually will cut out at this wind speed, which means they have peaked much earlier. And so if you had a combination of this, then you have a more uniform power output coming from your wind farm, which will be more acceptable. So as you already mentioned 50 gigawatt, and if we go as per plans, India could have I don't know, in the 450 gigawatt scenario for 2030, how much of that would be wind, but it would be substantial. And such things may be enforced by the regulators in future. So the other advantage with this arrangement will be, these low wind turbines are actually generating higher output during the low wind season. So I think this could emerge as a potential solution for future wind farms. Yeah, that's it from me, Vijay.
Thanks, Satish. Thanks a lot. That was very nice.
Yeah.
So now let us look at the new set of challenges that comes up. In India, we have been used to now providing maintenance cover, operations and maintenance cover for turbines in the sub 1 megawatt class. Maximum are in the 1 to 2 megawatt class. There are a substantial amount above between 2 to 2.6 megawatts. But we are now going to enter into an era where we are getting the 3 megawatt plus the 4 megawatt type turbines coming on onshore. And in a few years, we would be getting offshore also. So my question goes to Manjeet, because he's one of the experts in the O&M field, having handled the O&M in so many different companies, from Inox to Renom, Region Bartek, Enercon. How will technology help us in reducing the downtimes on these turbines and also on the older turbines? What are the new technologies and the impact of technology on improving our maintenance and reducing downtime?
Thank you, Mr. Vijay. First of all, it's a great pleasure to be here with these August panel members. And before I just start giving specific examples, what I like to say is that the design of the wind turbine is having a very important bearing on the reliability and availability of the turbines, because it also has the consideration of minimizing the manual intervention or the downtime due to O&M practices, and which will in turn result into the higher energy to the customer. So, starting from the blade, Inoxes, I would like to say, uh, is about to launch the 3.3 megawatt machine after this high wind season. The prototype has already on the way for the erection in the field, and this high wind season will be testing that. What some of the major features of this new design in the wind turbine as compared to our earlier model of 2 megawatt are there. The blade design has been considered. There is carbon fiber also has been introduced in the blade manufacturing. So it's a composite material, carbon fiber along with the glass reinforcement. The blade lightning protection system is further made very robust. It was already robust earlier, and our turbine enjoyed minimum kind of lightning related damages in the past as well. The ground resistance for the blades or my entire turbine system is less than 0.4 milli ohms. That's what we are maintaining, so which is fairly low value. On the gearbox and on the generator side, of course, the generator is DFIG. Being DFIG, it already produces. There is a maximization of power with respect to the copper content in the design, as well as there is also reliability factor in the generator. Uh, Gearbox is, of course, has been made more compact, and it is the cooling efficiency has been improved. On the safety system, I would like to particularly highlight is that the safety system, more sensors are installed, and more on the logic side and on the control side, the safety checks have been increased, by a good amount. And safety being paramount importance, because the concept is that the machine should not go to any overspeed or overheating mode, overload, and into any destruction mode. So there are various checks done preliminary before starting the turbine and before it goes to the load. So, and especially the pitching, for the pitching system, I would like to give example. The capacitors what we are using in place of the batteries, that design is also considerably improved to ensure that in no case or in no eventuality there is a during operation mode, like there is a continuous check on the healthiness of the capacitor bank. So which keeps on ensuring not just at the beginning of the trial run or at the beginning of the operation phase, even during the load phase and as you ramp up. So these are the various checks that are being introduced. Coming down to the converter panels, we have again modular concept there. So earlier it was like 50%. Now the modular is made further broken down into 3 power cabinets or 35%. So in case of any issue with the the turbine can come down to that load. Need not so the reduction in the load will be of the reduction load in the load will be very less. That is another safety feature. And of course, the cooling of the converter panels, helps in, of course, minimizing the failures to that extent. Uh, Coming to the operations part, we are all familiar with the predictive mode. So recently we had a tie-up with the vendor, and going in for a state-of-the-art machine learning based, artificial intelligence based software, really into the predictive analytics mode. So it just not only gives you it gives you like warnings and indications of the component level failure, and pretty much well in advance, so that you can prepare for the inventory, procure the right spare, and kind of arrange minimize your downtime. That is a really high end software, I would say. The trial runs are going on in part of the sites, and we are very happy with the performance of that. uh, Secondly, the design has been made so robust, keeping maintenance in mind. PM frequency has been minimized again. So we are now, we'll be doing 2 major preventive maintenance in a year. Of course, there is a third one there introduced, but which will be only a kind of a visual check. The main will be a one main PM, and the second one would be again not that extensive. So the number of days required for PM in a year per turbine has also been reduced by about 20 to 30%. That is another factor which we are considering. Of course, it is LVRT and HVRT compliant as per the latest CEA 2019 guidelines, so that there is no issues on the regulatory compliance point of view. The reactive power, I am told, is that drawback would be less than 2%, which is again, going ahead from what 3 to 4, what we are right now facing, even 5% in the older turbines, but this would be like pretty much, on the lower side. Uh, uh, Another thing what I would like to say is that on the maintenance practices, now this is not to do with the turbine design, but when we are doing any gearbox dismantling, we all know we have to use crane, and the crane has to face through the ROW issues and all. So with help of our existing vendor, we have developed craneless methodology for the gearbox, and we have done 2 turbines as on date. So that is, I think, a very big achievement. There is a significant reduction in cost as well as the hassles what we used to face, earlier. So I think this is the overall perspective from the O&M point of view. I have tried to highlight the majority ones. So in case anyone has a specific requirement, I will be happy to answer offline or even now. Thank you so much for giving me the opportunity.
Thanks, Manjeet. Thanks. Mr. Gopan, I've got a small question for you. We are seeing that, as was brought out earlier also, that the cost, if you look, almost 80% of the cost goes onto the blades, the nacelle, and the tower. So any suggestions for optimizing the costs of the tower and foundations?
Yeah, it's again, yeah, that's really an important thing because the cost is more. Say, if you ask me, the tower and foundation itself will be contributing to almost 30%. So definitely there is a scope. Because why I say scope, because it can be designed site specific. So that's why the scope is more there. Because blade you can't do site specific, it is done, so it is a done deal. So but the tower and foundation, there is a good possibility. Basis the wind condition, you can have a different tower hub height, we can think of. Apart from that, there are possibilities, like as we see that now each wind farm is coming to close to 300 megawatt. Then it is spread across maybe 25 by 25 square kilometer or 30 by 30. So in that aspect, we see it is not necessary that we need to have the same hub height for all these turbines. We can optimize that. We can have 2 or 3 different hub heights within the wind farm. So that way it is helpful. Apart from that, as I said, that the foundation also. Let me just finish the tower. Then the tower also now, see, we have seen different types of tower, whether it is a lattice tower or is a tubular steel tower. And then we have seen this hybrid tower where we have the lattice portion in the bottom and then the tubular steel at the top portion. And then we have the concrete, full concrete, and then concrete with an hybrid concept, concrete in the bottom and then tubular in the top. So what I see is that when we have like more than 200 megawatt of wind farm, exploring the possibility of using the concrete tower is also good. We can see that almost 20 to 25%, even 30% cost can be reduced comparing with the tubular steel. It all depends how the manufacturing will happen, and then closer to the site and all. So these all factors has to be considered basis that there is a good possibility for the tower to be a hybrid type, and that also helps. So on the tower side, there is a good possibility, and apart from that, foundation also it can be also designed site specific. It is because it is designed basis the site condition, mainly the soil bearing capacity, and then if the seismic level, whether it is 3 or 4 or 5, depends upon that. So it gives a good opportunity for a site specific design. Mostly we use this a slab type of foundation, which is a gravity based foundation that is generally used, but there are possibilities to go for maybe a wall or a rib type of foundation where we can reduce the steel and the concrete. So such type of possibilities are there. Apart from that, there is a possibility to increase the foundation, maybe something like a high rise foundation, so that you can reduce the steel, because you know that the tower, the bottom section of the tower, which needs a bigger diameter, and then steel consumption is more. It may come close to 90 or 95 metric ton, the tower bottom section itself. So the tower bottom section, if you want to reduce, because as we know that there is a logistic issue for the tower foundation, tower section also, maybe 4.5 or 4.6, or it can maximum go to 4.8. But then if the tower section diameter is increasing, logistic is also challenge. So we can explore the possibility of the high-rise foundation also with 4 meter or 5 meter, 6 meter. It depends how is the cost, economics or trade-off happens. So these are the good possibilities on the foundation as well as on the tower design. And basically, as I said, it can be done for a site-specific condition. It can vary from site to site. So we can definitely explore all these possibilities.
Thanks. Thank you. That was wonderful. So now we are seeing, that we are getting these large turbines, 3 megawatt, 4 megawatt. India will soon go to 5 megawatts onshore, and offshore, of course, much bigger. But onshore, there is a shortage of good windy sites. The best of the windy sites in India have the early turbines which came up, the sub 1 megawatt class turbines are having the best windy sites, whether it is in Tamil Nadu, in Gujarat, in Karnataka or Maharashtra. The best windy sites have got the small turbines. So there's a great opportunity for repowering, removing these small turbines which have reached the end of life. India is almost 27, 28 years into putting turbines. A lot of turbines have finished their life cycle or at end of life cycle. So there is a scope for repowering by putting larger wind turbines here. Now, as far as the tower and the steel structures, etc., the disposal is easy. But a challenge comes up when we have to look at the disposal of blades. So recycling of old wind blades is very critical for us. Can Rajiv, if he's here, throw some light on how recycling of used turbine blades is happening?
Yeah, yes, Vijay. I think this is a very important, very pertinent question in the keeping the current context in mind. As you said, India wind industry is now mature to the extent of 27, 30 years. So we have end of life blades coming down, getting decommissioned. So there is a lot of focus and a lot of strong commitment coming from the blade industry as well towards how to get into kind of a zero waste blade. That's what we are talking about. One is about the manufacturing waste, and the other part is the end of life decommissioned blades. Typically, the decommissioned blades are getting ended up in either landfills or getting into incinerators. So that's what we have been observing. The various other thought process which have been put into place in terms of sustainability, industry is strongly looking at how we can use the material in terms of getting reusing it, repurposing it, be in terms of industry or road laying or different areas where we could generally kind of get the value out of it. How to cut down waste out of waste is something what we are looking at, and it's a strong purpose, strong a lot of initiatives are kind of being thought about and getting tried as we speak. And I would say that it requires a lot of drive from the industry as well from the leadership of the blade industry to kind of get into this kind of a circular economy where we generally kind of come out of this situation and make the planet a better place to live for our future generation. That's a kind of a responsibility we all need to have. So the manufacturing waste is also something we are looking at, as we have seen a lot of waste as a byproduct comes out of while we make the blade, and that is where we put a lot of emphasis in terms of how we reuse that and ensure that what goes back or ultimately the disposal should be as minimum as possible in terms of the hierarchy of pyramid of the materials which come out of the industry. So overall, I would just like to wrap up and say that strong focus, strong commitment, and recently we have also kind of looked at how a kind of a sustainable recyclable blade can be launched. So we are getting into it, baby steps, but large leaps are required in that direction, Mr. Vijay.
Thank you. Thanks. So I think we have got time for one more question, and this was a question which I would like to ask Amol Korde because they are in the
Back to
design.
you, Mr. Vijay.
Yeah, thanks. Thanks so much, Rajiv. Thanks a lot. So this question is for Amol. We saw the blades, but there are now, due to this increased load, you're getting into giant blades, the increased load which is coming on.
Priyanshi, can you hear me? I'm done.
Yeah, we can hear you, Rajiv. Thanks. Amol, can you hear me?
Yeah, yes, sir.
So we are looking at huge rotors, 100 to 200-meter rotor diameters. So the gearbox design has become a very key parameter. The moment you go
Yeah.
above the 3 megawatt class, you're getting into huge gearboxes, massive planetary gears. The helical gear design has to be robust, and people talk of 3-stage, 2-stage, single-stage planetary gears. So, what are the challenges now that you're facing in these large gearboxes with respect to their design, and especially on the planetary gear design? And also, if you could towards the end touch a little on how uh, Naveen spoke on reducing the sound at the blade end, but what about reducing the whine sound at the gearbox and the generator and the overall noise of the turbine?
Yeah. The quick answer to the high power density gearbox is that it lies in the how you arrange the planetaries along with the final reduction gear set. Now, most of the time, planetary becomes really an art how you arrange in the sequence so that you get the maximum RPM out at the final stage. That is one thing. But secondly, is how you make the compact designs for and at the same time you get the maximum bending and contact safety factors and as well as the contact patterns itself because ultimately the gears are going to get bent the axis of the sun planets and rings they are not going to be parallel at all time so that misalignment considering that misalignment you have to compensate the micro geometry and get the contact patterns exactly at the center of the fly that is actually the key to have a successful gearbox design by which you can have more compact gearbox design and high power density. Answer to your second question is the noise coming from the gearboxes. It is not just the concern for the wind turbines which are commissioned on the land, but it is going to be more concern on the wind turbines which are installed in high seas or away from the seashore. The biggest concern is the ecological concerns, of course, because there are environmental legislations will be in place because the sound travels faster in water than in air. And with that physics law, we can see the gear vine and motor vine can radiate up to much larger distance in the seas, and that can really affect the ecology of the microorganism which is present in the sea. The remedy to address this noise issue is either you can minimize the sound source or you can then put the barrier in the sound source and the recipient. Here, there are two types of noises. One is motor whine and second is the gear whine. And the biggest concern is motor whine and gear whine, they are in chorus. They sing together. So in the design stage itself, you can have a staggered design for defining the electrical machine parameters as well as gear parameters so that you don't have chorus. And when you have isolated sounds, then you can actually apply on the electrical machine modifications to minimize the motor whine and reducing the transmission error, which is the source of a gear drive. So that way you can act upon reducing the noise both on the land wind turbines as well as on the wind turbines which are commissioned in the high seas.
Okay, thanks. That was a wonderful 2-hour session that we have had today, and my thanks to Wind Insider and First View for organizing this wonderful webinar. So we've had from Hexagon, Naveen, and Amol who have given us a great idea of what all goes into the design, the load calculations, the blade design, the gearbox design, the drivetrain design. We had Rajiv covering the advanced blade design issues, what is the latest in manufacturing technologies, how these large lengths of rotor blades are affecting the structure. He spoke to us on how the old blades are being recycled, or even the waste from the blade plants are being recycled. Satish gave us an insight. Satish Subbarao gave us an insight into upscaling. How what all can we do? How much more upscaling can we do on wind turbines? Any suggestions he gave on modular development of the blades? Some new radical design thought processes which are going on with the research engineers outside India on the wind turbine. And from PR Gopan, we got an overview and a good insight into how wind resource assessment is done, how you select sites, how you look at, in India, what are the good locations where all high wind season happens, better winds happen. And he gave us good suggestions on optimizing the costs of the tower and foundations. And from Manjeet, we got a lot of insights into how technology and electronics and data analytics and the whole SCADA communication system is helping us provide this cutting edge of technology in the maintenance of turbines. So, Priyanshi, largely we have done. Would you like to take it on from here?
Yeah, first of all, I request all the speakers to answer few of the questions in the Q&A box. They can add the answers as a comment. And thank you very much, all the esteemed panelists, for this wonderful session. And a very special thanks to YVR Vijay sir for superbly managing the session. Your industry insight and charismatic ability to engage both the audience and the speakers brought the session to live making and made them more informative, thought provoking, and as well as entertaining. So I'm sure if this would have been a live performance, it would have got an standing ovation definitely. So claps for you all.
Thank you. Thanks. Thank you. Thanks to all.
Thank you
Thank
everyone
you.
for extending your time and support for the event. We promise back to come with more exciting topics very soon. And your answers will be answered, your questions will be answered in the box itself. Thank you so much, everyone. Take care.
Thank you. Thanks a
Thank
lot.
you.
Thanks,
Thank you.
Thank
Bye.
you,
Bye bye.
everyone.
Bye bye.
Yeah.
Thank you, everybody. Thank you.
Thank you.